Welcome back. It's lecture 14 of our computational biology class. As always, I need to remind you that we're being recorded and live streamed. After we get through our presentation today, I want to come back and talk a little bit more about integrating network models into CompuCell. Last week, we talked primarily about network models that were freestanding. Of course, there's a lot to do about network models. There's a whole semester's worth of class and more that one can do about it. I can only show a small amount of that in this class, but I would like to cover a little bit of that material today. So let's start out then with the student project presentations, and then we will go into how to load and manipulate subcellular models in CompuCell and do a few exercises to practice doing that. In particular, we'll talk about how to load antimony models into cells, how to use them in the background, which is what we did last week. We'll do the delta notch example, which involves both subcellular modeling and interaction between cells, how you send information between subcellular models. And then if we have time, which we may or may not, I'll show you how to download pre-existing models. There's a beautiful database called Biomodels that has hundreds of pre-existing subcellular models in it. And I'll show you how you can download those and use those. If we don't get to it, then you'll have the slides and the documentation for that if you're interested. So why don't we start out with the presentation that we've got, and I will turn it over to you.
Yeah, I think I can talk a little bit about my project and Jackson's. We had set a goal at the beginning of this class a little bit too big. I think it was a little bit of an experience to understand how replications of papers work, but we got stuck in a bunch of debugging of papers, if we can call that, and trying to find, how to get the same rates for the results that they showed on their paper. Here, let me share this screen. This is so we changed a little bit of our goal now since we're in the last couple of weeks. This is the basis of the pyroptosis model. It would be the basis of the whole model, but implementing all the other cell types of death would take a little bit more time than just a week. So we think on just applying the rates to this model that is already working, not on the full potential, but in some level. And we just need to figure out how to get the rates or the Spml and antimony inside the cells, and that this class that we will have this week will probably help on that. One of the interesting problems that I was facing and I was showing Jackson about is the replication of the rates for that paper. Somehow the functions are not working correctly, and the mistake seems to be very silly. I know that this bug is something easy. For example, if we look at just the columns on this line and compared to the columns on that line, this is the only change needed to make these functions to work correctly. Not correctly, but I don't know even if it's better or not, but something weird is happening here. This is me plotting the actual equation, and we can see that the rate of change is doing what it's supposed to be doing here, but the actual amount of this molecule is somehow going negative. So
So one thing to look at there is the scale bar. The scale there is e to the minus 111, if I've read it right, which is 0. So the value, as far as I can tell, I believe the value is always 0. So one thing you might do there is actually, why don't you print the value? Print the final value of the parameter, of the variable. And you can't do that after reset all.
yep.
So you have to do it before.
And I don't remember the command in my head, but I think it's r dot and then the name of the, is that it?
Yeah. Yes. So that's 0. So all that that's telling you is that it's 0. There are always going to be numerical errors in floats. It's a little surprising that it would be negative rather than small positive, but 10 to the minus 111 is 0. So it's giving you a value of 0 as an output.
Yeah,
That
and
one there, I think is also 0, actually.
There is a way for us to print. This will show the value on the function at the last time. Okay. Yeah.
Yeah, so it's 0.
Too small.
So it's always 0. So all of those are 0. So now you have to ask the question, why is it 0 all the time?
Yeah,
that's also 0.
0. This is the only one that, okay. Yeah, here's the first thing that we noticed when I plug I reviewed this a couple of times. It doesn't get you 1, and they use 1 as their arbitrary values for everything. So one of the things that I can probably do is changing the arbitrary values to more than 1 to see if we can find bigger values.
Well, if the equations are what they gave, then you should get the same thing. So here the question is, the time scale is the same. The maximum values are a little bit different.
Yeah, I don't get you 1.
About, okay, so let's look at this. I don't want to spend too much time on this, but let's
Okay.
do this anyway. Let's look at your equation for NLRP 3. Okay. Which is the one that
Yeah,
which
these
is
are
the one we were just looking at, but which one is which?
This one is the is this
The green
here.
one is,
oh, the green one is O.
Fine, so let's look at the equation for O. So it is and it's not destroyed by anything, is that right?
No, it's not destroyed. There is no decay
Okay.
for it.
Okay. And you have something a little bit unusual there, which is why is NLRPA, why is the rate dependent on the square of the concentration?
Oh, they show a proof of why they do that. It has to do with some mechanisms behind the O here is oligomerized. So it has to do with how the time for every single activated NLRP3 takes to form the complete base.
So it's dimerizing, is that right?
Yeah, yeah.
So why isn't it 2 NLRP3A goes to NLRP30?
Why is not you? Yeah, I don't know. Here is the
Yeah, it's 2. Where is the equation for NLRP3A? Yeah, it's 2. Look, you're using up 2 of them there. Or rather, the rate is okay. So
it's true.
yeah, let's see. So you've got
We can do this debugging afterwards too.
right,
On a 101.
I think there may actually be a I think they may actually have a mistake.
Mhm.
Because normally when you see that squared, if it's dimerizing, then it takes 2 of the source to make 1 of the output. And so you would expect to see what we called stoichiometry, which we talked about last time. You'd expect to have the stoichiometric coefficients, namely the 2, be there. And whenever you see a rate constant that looks like the square of a concentration, you expect that.
I didn't think
Okay.
it dimerized. I thought it because it forms the molecules form together to create like a wheel, so there's more than just the 2 molecules combined together to create
Okay.
1.
Okay, but so I guess then the question is, how many of the O's do you get per molecule of A? If it's 1 to 1, then that's fine. Then it's right. But if you need multiple ones to, now that's not going to change. Probably that's not going to change the result in the sense that the scaling should still be.
Yeah. Let me get the paper here. We can, yeah, as I said, we can do this another time, but it seems it's 6, 7.
Okay, so then it's a little bit different. So, but there is a question: is what determines the maximum value? And that maximum value is going to happen. But if we go back to the equations, let's go back to even to your
To the antimony.
Yeah. So we have in the equations that you have here, NLRP3A decays.
Mm-hmm.
NLRP3A also becomes NLRP3O.
Yes.
So you can't wind up with more NLRP3O than you have NLRP3A.
Yep.
And the faster the decay rate is, the less will eventually become NLRP3O. You start out with I turns into A turns into O, okay? If you had no source, you would expect, and there were no decay, then eventually all of your NLRP3I would become NLRP3O.
Mm-hmm.
The fact that you have decay means that you won't get all of that. On the other hand, you also have a source, which is NLRP3I is being created.
Mm-hmm.
And that rate of creation is independent of all of those species, right? It depends on NF kappa B, depends
Yes.
on, but that's it.
Which is
And
correct if we look at the 2 things. This NF kappa B is correct, yeah.
and so, and those are not variables, is that right? Those are parameters?
Yeah. Here's the function I can show you. The function should do this. It's doing exactly the thing, and it's written
Right.
down here.
Right. So the area under the curve, so the total amount of NLRP3I that you create can't be more than the area under the curve of that function. And so that's going to limit how high everything else can get, because you have to think about the flow. This is, and I'm trying to go over this because I think this is important for everybody. You want to think about the flow of mass in your system. And mass is coming in when you create something. Whenever you have nothing goes to something, you're introducing mass into your system. Whenever you have something goes to nothing, you're taking mass out of your system. A goes to B is mass conserving. And so you want to ask the question, in this case, NF kappa B is providing all the mass in the system, because that's basically controlling the production of that first term in that sequence. And so you could ask the question, what was the total amount of type A that's created? Well, if we go back up to your, let's go back up to your equations for the moment.
Right. I just wanted to ask you, so this would be impossible here, since there's also never get to 1. So having a production,
it's the area under the curve.
Under the curve, the whole area. Okay.
Right. So I don't know if it's scaled to be that. So let's check that. The way to check that would be the following. Let's turn off everything below the 3, 2, everything. Let's just look at the I. Let's see how much I is created.
Okay.
And we're going to do that by turning off everything that gets rid of the I term. So scroll up. Don't move around too much. Comment that one out. And comment the next one out. Okay, and now we're creating I, but we're not getting rid of it. So let's see how much I is created, because the maximum of the next two cannot be larger than that. Okay. Why don't you run that and just look at the I? Okay, so that goes up to 0.7.
Yeah.
65. So you can't ever get to 1. So something is different here. If you look at your parameters, if you go scroll up again, either the prefactor A1 is different, it's smaller, or the time series for NF kappa B is slightly different.
Okay.
You didn't replicate their time series exactly. But once you've gotten that, everything else will scale off of that. And so you could divide by. So now you could. Let me just show you a sort of not a very pretty trick, but let's do it anyway. Let's replicate the line. What we're going to do is the following. Let's scale everything by that maximum possible amount.
Okay, which is from their example. Oh,
no, from yours.
From Mars. Okay. 0.7.
Right.
Okay.
So what you could do is you could actually get that number. You just divide by points, but 0.7 is fine. So now, if you turn on the decay again. So turn on the decay, and now run it. See, now you're going to lose it.
Yep.
Although you're losing it fairly slowly.
Yeah, if I'm not wrong, the decay is slow, and here is 0.02.
Right. So the lifetime is 500 minutes. Okay. And now you can keep. I mean, you could keep going, but you want to walk. Again, as a matter of practice, and this is something we didn't really cover so much, I really encourage people to try to build things up one step at a time. So if you have a chemical reaction, look at the first step in the, especially if it's a sequential chemical reaction. Look at the first step short circuit, turn it off after the first step. Make sure that that behaves the way you expect. Because let's turn on the J233 now. Okay, now look at just I. Does that replicate what you expect for I?
Yes, it does. Here, it's almost the same. The I is the dot. Yeah, it's almost the same. I mean, they have different scales, so I can do like what
Right,
I
so I
limit.
would, use their scale.
Yeah, 0 and 2. Oh, it's not I limit. Did I do something different?
Is it Y scale?
I don't remember how to do this from my head.
If it's Python, it should be Y limit. Maybe it doesn't like the square brackets. See,
Oh, yeah, I think I forgot the equal. Yes, but now it's a different.
Okay, but that's correct. That's what you have. So let's
Okay.
look at. Okay, so now
Yeah, it's basically the same that they had. Yep, it's dying on the 50. 50 is around here.
yours is a little faster.
A little
that's why.
faster. Yeah.
So you need to walk through it, and of course it would help if they had better, more ticks in their scale bar. But it looks to me like your NLR3B3A looks about right. Peaks out at about 0.2, a little below 0.25 at about 10 seconds, 10 minutes. Looks about right.
And
And so it
then
looks like then the conversion to NLRP30 is different. So it looks like it really is that production of that's the issue, which means that the prefactor has to be different.
yeah.
So I would try to walk through it step by step. But again, if you can't replicate their result, then you report that you can't replicate.
Yeah, that was another thing that we were discussing. If that can be part of our project, just being, I'm doing these reports as I did for the other one. So finishing this, if that can be part of our project, even though we don't have the correct rates, we can use all arbitrary rates, but show that we try to replicate a paper that had rates.
Well, what you do is you show what you got using what they said they did.
Okay.
And then if you show that their model with their parameters doesn't give you what they said it did, then you have to try to figure out what happened. The most likely thing is the parameter values are wrong. The second most likely thing is that the equations they've given you are wrong.
Okay.
If they published their code, you could go in and look at their code and see what they did, which isn't the most convenient thing in the world. But Connor, maybe you could comment on exactly what was just being discussed. Because I think we had exactly this experience earlier today, didn't we?
in terms of comment on which part?
Well, you had a situation first where it was complicated to replicate.
Right.
But then when you looked at the equations in the paper.
Oh, yes, that part. Yeah, I mean, my experience with this stuff is that, especially even just this semester, is that sometimes when people are typing up their documentation for their equations, it's pretty often that a parameter is off. So today when I was working with Professor Glazier, we found out that the equation where they described how they were calculating the binding energy, was not what they showed in their figures, and also did not seem to line up with what was described verbally, which means that it's not, I mean, it's sad, but it's not uncommon for either the math to be off or for the math to be right, but for the equation that they put in to be not actually the calculation that they did.
So then we looked at the code.
Yeah.
Now, you should not have to be wading through Python or C++ to figure out what they did. Right? Their description should be correct. But in fact, people don't like to repeat themselves. So there's the equation exists once in the paper. And if they left out a 1 minus, there's an issue. And the same thing with parameters. It's very easy to have a decimal point in the wrong place or accidentally copy the line above the line that you wanted. And there's no way to recover that. That's irrecoverable information. Now, if the code happens to work and be embodied in a way that makes sense, and you can dig into the code and see what the parameter values were, or see what the equations were, then if their code actually runs and gives the result, the code is the authoritative thing. But that's not, you shouldn't have to do that. And so part of the motivation for this, and I realize it's painful, is so maybe if you go forward and you start publishing models, you don't do this to people. It's a hard way to learn it. But as I said, we work with Rahman Sharif in the UK, in Cambridge, and his specialty, he creates this biomodels database, and they studied 500 papers of network models, not as complicated as these multi-scale models, but just network models. And they could replicate less than half of their published papers. And that's appalling. It's maybe not surprising, but it's appalling.
Would you be able to send the name of that paper or a link to it? I'd be interested in seeing it.
Yeah, I don't regret any time on like trying to replicate these papers, because as you said, I learned so much about how science is done, and it was probably naive of me assuming that replicating a paper would be as easy as I was imagining, and this has been eye-opening.
So this is the, I don't know if I'm screen sharing the figure. Okay. So this was their basic result. Are models directly reproducible? Yes, 51%. So I was slightly wrong. They could reproduce 51% of the published work. And this was all papers that included the code. So this wasn't even something where it was just, by the way, they didn't give you the code. This was papers where they included the code, and it still didn't work. And then an additional 12%, they actually asked the people who did the work to help them, and only 12% additional were able to replicate their own work. So, and these are pretty simple models. So anyway, I shared the link in the chat. All right. Okay, anything else? Anybody else want to go over anything? We don't have to do formal presentations, but if anyone wants to discuss projects, problems, anything else, we have a chance now for a minute.
So one thing that I was thinking about was the implementation of the formula in the adhesion flex steppable. I know that it's possible to go to the C++ code and maybe like change something in this mu parser that converts the formula into like some sort of super fast C++ code, because we would need to implement like a Hamming distance and a bunch of other I guess conditions in our formula. And I think that you know, as I guess Connor showed you earlier, that I was kind of able to go around those limitations, but you know, if I knew how to kind of make a modification to that parser, it'd probably be a lot easier.
So the answer there is you sure don't want to be rewriting mu parse. So if I were going to do that, what I would recommend doing is taking the regular adhesion plugin or the adhesion flex plugin and cloning it and creating a custom C++ version of it that implemented the specific algorithm you wanted. And then the question a little bit is, so CompuCell is, in this class, except for Alex, who's been digging into CompuCell internals in a big way, the whole point of CompuCell was so you didn't have to write C++. And CompuCell, actually, Twinit has the functionality to help you write C++ components, just the way there are code snippets for Python and code snippets for the CC3D-ML. There are code snippets also for C++. And depending on what you're trying to do with the C++, it's never easy. And there's an issue that you have to compile CompuCell, which is in itself not a lot of fun because it's a big package. But we can certainly help with that. The biggest problem when you're doing things like energy functionals, and this is something you don't face if you're working with Physicell or Tissue Simulation Toolkit or any of the other C++ hard-coded packages, is that CompuCell is flexible. And our plugins are written to be able to accommodate two-dimensional and three-dimensional calculations, to be able to accommodate square lattices and hexagonal lattices, to be able to accommodate any arbitrary interaction range. And so if you essentially want to hard code a method that you're going to use for yourself, implementing that in C++, beyond the compilation annoyance, is really not very hard. If you know you're going to be on a square lattice, you're going to be doing next neighbor simulations in 2 dimensions. Implementing an energy functional in that in C++ is not much harder than writing it. It's a few lines of code. If you want to write methods that work for arbitrary ranges, 2D and 3D and square and hex lattice, then you have to basically write versions of your code for all of those cases. And so the problem with doing the C++ is if you wanted to distribute it as part of the core CompuCell package, then we typically require that with a very few exceptions, we require that the code work that it not break when the user changed those settings, because those are legal settings in the code. And so the biggest obstacle to writing C++ for CompuCell is making it distributable. Doing it for yourself to accelerate things is not a problem. And talking to Connor today about those energy functionals that you wanted, it wouldn't be that bad to do it. Now, MuParser does compile. That's why they use it. But you could certainly write a more efficient version of that particular algorithm. That would be a lot faster. And so if you're going to stick to 2D square lattice second neighbor, implementing that in C++ would be, you could sit down with TJ or Giuliano, and in an hour know how to do it. And occasionally we do get people who write custom C++ packages. There are a few Easter eggs in CompuCell of that kind, because we don't, if it's not universal, we don't advertise it. We don't distribute it. Well, distribute is the wrong word. We don't advertise it, but there are in fact a few functionalities where somebody wrote a C++ DLL, asked us to put it in, and it's there. In fact, there's a new one in the current release of CompuCell, but it's not in the manual. Our friends at the EPA wrote it. They need it for their code, so it's there. But unless you know it's there, you're not going to find it. And I know that there are things that are supposed to be findable that aren't described in the manual. So the fact that there's something missing from the manual won't surprise you too much. But there it is. So if you wanted to do that, that would be good. Andy, when he worked with us, did a lot of JIT compilation. And the SPML solvers work that way. They JIT compile. And they're very fast. Those SPML solvers, they may seem slow when you run a lot of them simultaneously, but if you compare the solvers for the SPM, the Antimony in our code with what other people use, we're a lot faster, and it's because it's JIT compiled. So that's not C++. That means learning a different set of languages and compilers. But that is possible. And the problem with energy functionals is they're in the innermost loop of CompuCell, right? Because each Monte Carlo step, if you're on 1,000 by 1,000 lattice, you call that function 1,000,000 times per time step. If you're on 1,000 cube lattice, you call that function 1,000,000,000 times per time step. So if it's slow, your code will be really slow. And so that's another thing that comes up when you want to do those energy functionals, which is CompuCell is multi-threaded, and making sure that your plugins are multi-thread safe, or at least there's some issues that aren't fully safe, but are not too bad that way, is another thing to think about. So but if you're interested, I promise you, Maciek and TJ would love to show you how to do it. And I apologize if I didn't cover this material in this class. But if we were sitting in the computer science department, it was really a coding class, I probably would have done that.
Yeah, I think one of aside from all the molecules that we have in our adhesion flex, I think a big point of the slowdown might be the multiple conditions that we have in this statement. Just given, at the low level, if statements are a slowdown code in terms of branch prediction.
Yeah, every time you lose your pipeline in your processor, every time you do a conditional, at least if the conditional fails. If it's successful, sometimes they'll write it pre-computes and then assumes it's a yes, but yeah, it'll break the pipeline every time. So that's an issue, and there's some things in the way that, ironically, and I don't want to take too much time on this, to do the specific things that paper wanted to do conceptually, you could do with adhesion flex as it's written, but the particular way they chose to implement it in that paper is strange. And so it's not a very good match to the way we did our adhesion flex. And actually adding that capability, right? Our adhesion flex plugin says if molecule 1 on cell 1 and if you have molecular species A and molecular species B, and they interact, their behavior is what it is. And that's independent of the type of cell that those two species found themselves on. And that's biologically pretty much true. But in the paper you're replicating, it's not true. Molecule A on cell type 1 and molecule A on cell type 2 behave differently. And so that's not built into that plugin. And an extension of that plugin that allowed you to have conditionality in the C++ on the cell type as well as the molecular species would not be a hard extension to do. It wouldn't be easy, but it would take a day or two of work to write a plugin that did that. That was completely general. And that would be a super valuable thing to do. That would be more of a project like the one Alex has been doing, which is an extension to the core code. But that would have been, I think that was actually an option that was presented in the list of possibilities with creating a new plugin. And so I certainly don't think that would be a bad thing to do. So maybe in a future year, if you want to come back and try that, you'd be welcome. We'd love to have it. And I hadn't appreciated the need for it so much until I looked at this paper. Other comments, questions, suggestions before we move on? Okay, so next week everybody is going to be ready to present, right? That means something that they can demo. It means a talk.
I haven't gone in detail through the Canvas thing, but did you have like a time, like how long you want us to give each of our talks to be?
Well, there's 6 people and there are 4 groups. And we have in principle 3 hours. In practice, people always take longer than they think. So if I said try to take 20 minutes to half an hour, then I suspect that will chew up 3 hours. I'll have some additional material to present in case we run out of things for you to present. But I think, and I know it's also unhelpful. It's like, how long should it be? And the answer is as long as you need. I mean, somebody could do a beautiful piece of work they could present in 5 minutes. They picked a paper, they replicated it, it was simple. They saw the result, it worked fine. They've got a beautiful demo. They have 3 sliders, they show it, and that's it. Or it could be something complicated where it takes time to walk through it. So certainly don't talk for an hour. But do take the time you need to present your ideas and your results. And since you're presenting code, you might talk a little bit about the background of what MPI is. If you're going to show GPU work, you might say what CUDA is. You might show some code examples, not all of your code, but a few code examples, and explain a few things so that we're not talking about C++ so much in this here or the particular libraries, but enough that somebody who wanted to learn about it would understand what the challenges were and how you solved them.
We could walk through 3,000 lines of C++, but do a code review to take up 3 hours.
Right. I'm not suggesting that, but there were probably some interesting problems you had to solve. And showing a couple of examples of that and how you did it would be great. I think we'd all learn from that. I mean, I've been with TJ working with it hasn't been C++, it's all been Python, but TJ's been working with this undergraduate Trinity, and she's been writing these graphical display modules for CompuCell to work inside Jupyter Notebooks using Jupyter Notebooks VTK integration. and the issues about how callbacks work and how those graphical interactions work was something that was pretty unfamiliar to me. And so actually learning, seeing examples, seeing how it works, walking through the code was very helpful. We were working with another student who's using the logger function in Python. And you think writing out an error log is simple. Well, the logger function is really rather sophisticated. Painfully sophisticated if all you want to do is write out a single file. And the way it happens to interact with player is interesting because within player, when you hit stop, it doesn't create a new logger instance by default. Logger is persistent. And so even though CompuCell then creates a new directory, when you hit stop and start again, it creates a new directory and a new instance of the simulation execution. Logger happily will continue to write to the original directory. And so your log file is, where's my log file? Well, it was appended to the original log file the first time you ran player. You can get around that, but it actually is pretty tricky. And so those kinds of things are, even if it's not in the context of CompuCell, it's good to sort of see, oh, wow, if I ever have to do kind of error logging, there's this great package, but it's not so simple to use. And so both MPI or OpenMP and CUDA are things that people may very well want to use. They're not going to teach a whole class on them, but giving people a flavor for the issues and the ideas, I think is really great. I'm not a heavy coder these days typically, but I enjoy seeing how these things are done. And help if you can help us catch up on the current state of the world, it would be much appreciated. Does that help? Okay. All right. Anybody else before we move on? And the other thing I'll say, I'm not encouraging this, but if you need to take it incomplete to finish things up, it's okay. But tell me in advance, please. So, and I strongly encourage people not to take infinite incompletes. I realize in project-based courses, there's a temptation to do that. Finishing up incompletes is time-consuming sometimes. So I roomed, then I'll move on to real work. We'll cut this out of the edited doc. But I roomed my first year of graduate school. I roomed with somebody who's currently a professor at McGill. And he had a complicated history. He was a genius. And if you look at his CV has 4 degrees on it. And the degrees are in order: a PhD in mathematics, 1st degree, a bachelor's in philosophy, 2nd degree, a bachelor's in mathematics, 3rd degree, and a PhD in philosophy, 4th degree. And the reason for that ordering was incompletes. So he concentrated on finishing his PhD thesis in mathematics, which made sense, but that meant he never went back and finished the incompletes for his undergraduate degrees. So he's the only person I know. I mean, I could imagine having a PhD in a subject and then going back and doing a BA in a subject, a different subject later on. And there's a somewhat eccentric person here in Bloomington who teaches at Ivy Tech, who has 45 mostly online master's degrees. He collects them. He finishes one, he starts another program. There's 45 degrees. Some even in the same subject from different universities, but mostly in different subjects. So that's fine. But to get a PhD in mathematics followed by a BA in mathematics, to me, is truly eccentric. So I recommend not doing that. There's also a university rule that if a incomplete lasts a year, you get an F. Now, if you then do the work, you can undo the F, but having a fail on your transcript affects things like financial aid. And so I really encourage people, if you need a few extra weeks or a month, that's fine. But to have to come back to a project a year later to finish it up is painful. So I'm not trying to force you to finish something you're not satisfied with. I'd rather you take the time to do it right. But please don't hang yourself by using that flexibility too much. Again, our goal is to learn. But I do. Sometimes being flexible is a bit of a trap. And I don't want to have you have a problem because I'm flexible. Right. So let's come back to where we were. Last time we talked about biological networks. I mentioned that biologically, there are 4 kinds of networks that we're going to deal with: chemical reaction and metabolic networks, signaling networks, regulatory networks, and then whole body, or what are called pharmacokinetic networks. They all are networks in the sense that you have nodes that represent concentrations or amounts of materials. You have arrows that represent mass transformation or mass transfer, sometimes other arrows that represent regulation. And you'll find, as always, that there are lots of notations. The great thing about standards is there's so many of them. But there is a basic fundamental similarity in the mathematical underpinnings of these that will be shared, and means that you can use the same kind of formalism to represent all of them. Biologically, the time scales and length scales over which these operate are quite different. The fundamental mathematics, as I mentioned, is going to be a concept of a rate equation. Here I have molecule A combining with molecule B to make a molecule C. Carbon and nitrogen coming together to make cyanide, for example. The arrow has a rate on top of it. Typically, those rates depend on the things on the left-hand side of the arrow, on the source side of the arrow. And that one arrow diagram, which is how a chemist would write a chemical reaction, translates into 3 first-order ordinary differential equations: 1 for the change in concentration or amount of A, 1 for the change in concentration or amount of B, 1 for the change of concentration or amount of C. And so we do have to get used to going back and forth between the ODEs and the arrows. And as I mentioned last time, I'm a big believer in the arrow diagrams, because the arrow diagram unambiguously translates into rate equations. The rate equations do not unambiguously translate back into an arrow diagram. We might want to know if we can say something about what the rate law is. In the case of a simple chemical reaction, we often assume something called mass action, which is that the rate's proportional to the amounts or concentrations of the components. I haven't done all of the analysis here, but in the specific example, for example, Joel was showing, if I had A plus A going to C, that is 2 molecules of A combining to C, then I would have K times A. I'd have Ka squared. And so typically, stoichiometry, the number of times each molecule has to combine, shows up at a rate law as the power of the concentration. In reality, there are all sorts of things that modify those kind of simple rate laws, but those bilinear rate laws are pretty typical. The other thing is that in reality, molecules are not continuous, they're discrete. If we're talking about oxygen or water, there are plenty of them, and so treating them as continuous is not a bad approximation. If we're talking about DNA, there's 1, or most a couple. And so, in fact, this rate, this equation is something is 2 molecules are floating around. At some point, they encounter each other and react. And if that frequency of reaction is low compared to the time scale over which we're looking, we probably should be modeling those reactions as discrete processes rather than continuous ones. And it's not really accessible in CompuCell. In principle, you can do it, but it's a little bit tricky. And I'm not going to do it here. But antimony, tellurium, and the solvers in CompuCell do have stochastic solvers. And so if you want to say one molecule of A combines with one molecule of B stochastically to make a molecule of C, the standard algorithm for doing that is called Gillespie. And that will give you a probabilistic stochastic process, much like CompuCell. These CompuCell layers are like that. The reason it's not so implemented here at CompuCell is because it's slow. Gillespie solvers are slow. And so if we're going to run thousands of copies of them, it gets painfully slow. And usually the stochasticity of the CompuCell layers is sufficient that you don't have to worry so much about the stochasticity at the molecular level. But that's not always true. When people are interested in that, that's something we could talk about. Okay. I talked a little bit about arrows and signaling networks. I talked about this idea of regulation. The basic chemical reaction arrow is still the one with the pointed end. But in signaling and gene regulatory networks, you have the idea of something that modulates either a lollipop arrow, which is called an activator, or T-shaped blunt-ended arrow, which is called an inhibitor. And the idea here is that the more A you have, the faster S1 becomes S2. The more R you have, the slower S1 becomes S2. In general, A and R are not used up in those. They're behaving as catalysts, essentially. And so if we see the arrow diagram of a regulated reaction, we have to interpret that as a chemical reaction. So we have to do some mental translation to go from the arrow diagram to the equation. For a pure chemical reaction, the arrow diagram turns into tellurium or antimony immediately with no mental gymnastics. In the case of regulation, we have to think about it. Same thing in the case of a gene regulatory network. Here, classically, the notation can either be very sparse. P1 promotes the production of P2 with no information about what's going on. I'm afraid that shows up quite a bit in the world. We have to interpret that as P1 binding to a promoter site on the gene, turning the transcription of the gene on. The transcribed gene has to then be translated to produce the protein, and that protein itself will eventually decay. And so this single lollipop arrow, P1 goes to P2, actually turns into 2 chemical reactions plus a regulation. And again, we have to have some idea about how rates go. Typically, regulatory rates are assumed to be Hill coefficients, that is sigmoids, where if you have a promoter, for small amounts of the promoter, the rate is low. For large amounts of the promoter, the rate is high. The rate saturates. There's a limit to how fast you can transcribe DNA. Can't go faster than that. And you ask the question, what is the concentration of promoter at which the rate of transcription is half of its maximum? That's K1. And how steep is the turn on? The cooperativity, so-called cooperativity, which is N. And again, if you're interested in that, come back next fall, take E340, 540, you can spend a semester talking. Remind you that I sent you the handout, the cheat sheets. For tellurium, there's the great documentation that Herbert's written that I recommend. Always recommend having that available to you. Then we talked a little bit about antimony model specification. The antimony language is quite simple. We haven't talked about all of it. There are a lot of options which we don't need so much in this class, but which are available. One of which actually is shown in the example on my slide. That was a Freudian slip. This $sign here means that the species is a boundary species. It means S is kept constant, value of S is kept constant. But the basic idea is a named reaction, E0, colon, source, sink, rate. And that basic idea is pretty straightforward. We could have nothing going to R1. We can have disappearance, Q goes to nothing. But basically, something goes to something else is our basic idea. We need to specify parameters and initial conditions. As I mentioned, we can do conditionals inside of antimony. It's not hard to do that. We can do things that are a little bit more elaborate. We can do function definitions. We can do piecewise linear functions. We can do a variety of fancier things. Most of the time, we don't use those so much in CompuCell, but they are available. And again, they're well documented. They're on the cheat sheet if we need them. The key thing from a CompuCell point of view, which we'll come back to today, is that once we have a model loaded from antimony, immediately the model variables and parameters and the rates are available as dictionary elements in CompuCell. So if we create a model and that model is loaded in CompuCell as a whole, what we call a free-floating model, we can reference its components, self.spml.model variable name. If it's loaded inside a single cell, cell.spml.model variable name. In the old days, antimony was case insensitive. Now, like Python, it's case sensitive, so you have to watch out for case. It's very easy to, if you have long names, to have one lowercase letter, and that can cause a mess. You could say, why does it say SBML here when I keep saying antimony everywhere else? And the answer is that there are a number of standards for writing these kinds of reaction models. Antimony is a great way of representing them in human readable form. SBML is an interchange standard. It's a markup language, given the ML, which expands this definition into something that is more computer structured. It's also as a language developed by Herbert Sauro. It's used by many, many thousands of people and hundreds of different packages as an interchange standard, but it's not really human readable. Well, it's human readable, but it's not much fun to read. It's designed as an interchange language. Actually, SBML is much older than antimony. CompuCell supported SBML before it supported antimony, but it uses the same solvers and interface and APIs. And so you'll see SBML show up when we're talking about antimony. So just to remind you what an antimony string looks like, typically we will create a model string, which is going to be a Python string. We'll put it inside of triple quotes so we can have carriage returns in it. Remember, we can use comment. We can also use hash instead of the double slash for comments. Semicolon is the line break or section break. The fundamental idea is the rate equation. Doesn't have to be named, although I encourage you to name them. Something goes to something with an arrow. and then a rate law. As I mentioned, if we have real chemistry going on, 3 molecules of A and 5 of B combined to make 1 of A, 2 of C, and 9 of D, keeping track of all of that by hand is a pain. Antimony will handle it automatically and make sure that it subtracts the right number of each species and adds it back in the right way. We have to remember that the exponentiation operator in antimony is the caret rather than 2 stars. That's another easy mistake to make. We're allowed to have dangling sources and dangling sinks. We've seen that already today in the examples we've looked at. We can write ODEs directly with a apostrophe. T apostrophe equals beta times T times V is dt by dt equals beta TV. That's equivalent to writing an arrow goes from nothing, goes to T, semicolon beta times T times V. Gives you the same result. It's important that we specify all parameter values. If you're missing a parameter value, you'll get an error. Variables typically default to 0, but you need to be a little bit careful about that. So it's better to specify initial values for everything. All right. Something that we didn't mention so much, but that we need to come back to now is that while it looks, let's come back to this. Let's come back to our code for a moment. Our code example. This one isn't a good one. We need one that has more stuff in it. This one. Our code example here, we have S go to R go to Q, Q go to nothing. That order makes some logical sense because we see S creating R going to Q, Q going to nothing. If I exchange the order of the E0 line and the E3 line, would it change anything? When I execute this code.
No, because the compiler will read everything, and
right. So one of the things that we have to think about is that this looks like a programming language, and it is a kind of programming language, but it is what's called the declarative programming language, rather than a procedural programming language. And so, in general, the order of our lines doesn't matter, although there are a few exceptions to that. And those have to be thought about. But what will happen in Tellurium or in CompuCell is that this model string will be read, it will be compiled, and that compiled program will be executed. And what that means in particular is that things like these initial conditions are evaluated once when the model is compiled and not looked at again. And so if I write a code like this, J1, A goes to B, right? K1 times A is 0, B is 0, K1 is 1, C equals 3 times A. The value of A could change in time. The value of C will always be 0 because the initial value of A was 0. And so just the way in C++ or Python, we have a distinction between equals as an assignment and equals as checking for equality. In antimony, we have a difference between a single equal sign, which represents initialization, and colon equals, which tells antimony that this is a functional assignment, and therefore the value of C has to be updated when A changes. And that's a very easy mistake to make. It's very easy to type C equals 3 times A, and then wonder why your code isn't working when you needed to type C colon equals 3 times A. It's also easy to make the opposite mistake. If you type colon equals when you really wanted that initial condition, you'll have a problem, because one of the things that's nice about these procedural, declarative languages is that we can overload parameters very well. We want to run the simulation where K1 has a different value, where the initial value of A is different. We can change it outside of the model specification. If we say C colon equals 3 times A, we can't change C anymore, because it's now assigned to be whatever 3 times whatever the value of A is. We can't override it anymore. And so again, the external behavior of the model will change when we use that colon equals. C will behave like a variable. And so this is something that I haven't shown you how to do function definitions, for example, inside of Antimony. You can do it. We haven't really talked about events. But this one is something that people can get in trouble with. And there are a couple of places where it can be rather complicated. You can wind up, there are certain situations in which you can't use C when you might expect it to be usable. And so I'll just warn you about that possibility in advance. Again, for our purposes, we're not going to fuss about it. So what we haven't done so far is build any simulations which actually use the potential capability of network models inside of cells. And this is a simulation I showed at the very beginning in the first lecture class. It was a simulation done by Giulio Belmonte, who's now professor at North Carolina State University, Susan Hester, back 10 years ago. And in this case, we have individual cells simulating the cells in the presemitic mesoderm of chick. Each one of these cells runs what's called a semitic clock. It's a set of biochemical oscillators, there's signaling networks, and also gene regulatory networks. And here is the ODE version of this. Really should be arrows rather than ODEs, but it's ODEs. These ODEs are implemented in Antimony and running inside each cell. Those cells interact with each other through contact. They also interact with a chemical field in the extracellular space that modulates these reactions. And that leads to periodic gene expression, which you're seeing here on the right-hand most column. That is expression of a molecule with the wonderful name of lunatic fringe. And that lunatic fringe expression then leads to cell differentiation, changes of cell adhesion, and reorganization. And so this is the kind of real multi-scale integration that we'd like to be able to do. We're not going to do anything that fancy today, but conceptually, once you've done a simple example, you have more molecular species, more interconnections, but the concepts are all there. Another example here, which is one we may do at the end, is the regulation of cell division. In this case, and this is actually one of the demos that that's going to be a project, class project. This is one of Tyson's models of the cell cycle. Here we have individual cells. Those cells are growing. As they grow, that cell cycle model reads the volume of the cell, and that affects the oscillations of the cell cycle genes and triggers cell division. So far, when we had cells divide, So far, when we've had cells divide, we've had them divide when they reached a doubling volume. In reality, that division is triggered biochemically and may or may not have anything to do with the actual volume of the cell. And so it's interesting to be able to work with that. Another one, which I hope we will do today, is this delta notch example, where the cells have an intrinsic network, and they are also sending signals to each other. And so the state of that internal network of the cell depends not only on its cell itself, but on the state of its neighbors. And that one, as I say, I hope we'll do as an exercise today. So those are simple examples. If we're going to do this kind of integration, the first thing we have to be able to do is specify the network model that we want using Antimony or another language. There are other languages that CompuCell supports. There's something called MabBoss, which is relatively new, which does Boolean network models, stochastic Boolean network models. There's something called CellML and Spml, which I've already mentioned. Once we've specified the model, we have to be able to load it into either the whole simulation or individual cells. Once we've loaded it, we have to be able to time step it. We have to be able to connect those network variables and parameters to CompuCell variables and parameters. We'll do that by exposing them through the dictionaries that we talked about. And that does require a little bit of glue code. It's not something that's automatic. For example, if you want to couple variables between cells, we're going to have to do some glue code. And then something else that we can do, which often we don't, but in complex models is useful, is we want to be able to unload and clone network models. It's not that you can't leave a model in place when you're not using it, but if the models are very large, there's a cost to time stepping them if you're not using them. And so you want to unload them. CompuCell has a variety of ideas of scope. Potentially, you can load a network model into every cell. You could load a network model into all cells of a given type, or you could load a network model into just a single cell. You're also allowed to have multiple network models inside a single cell. Those are all allowed. You have to be there's nothing even to say. I was going to say you have to be careful. You don't really have to be careful. All of those are possible. I mentioned loading by cell type. Loading free-floating model is the model that runs in the background, which is the one we've done. Connor, go ahead.
I was curious how difficult it is to integrate with like an external field like we've been working with, like either to get them to excrete or to have the chemicals that they take in impact the antimony equations. Is that something that works?
Sure, that works. It's not, but it's not automatic.
Okay.
You have to write some glue code. So typically what we would do is we'd say, suppose you pull a chemical in from outside. You do that uptake. You'd use the secretor to do uptake with total count. You'd convert the amount that's pulled in to the units that you used in your antimony simulation. And then you would add that amount to the internal representation. Similarly, if you want to do secretion, we would take the internal represented amount of a molecule. We would use the secretor to secrete it out, and we'd take that amount out. But the bookkeeping we do have to do by hand. We have to take we take the amount in the variable, we subtract it, and we then secrete that amount outside. But that's something we do a lot. It would be nice if you could draw an arrow and have it done automatically the way it takes care of it inside of antimony. But we don't have that. We've dreamed about that kind of workflow where you draw the arrow and it does that. But we don't, at the moment, you have to do it. If somebody wanted to write that code, it would be nice, but reasonably, the number of possibilities is large, so it's not so trivial. There's a beautiful modeling framework called Morpheus from friends of ours at Dresden, which is also a POTS model-based simulator. And instead of using Python, they wrote their own scripting language, which was a lot of work. But one of the nice features of that scripting language is it does have that idea of connectors built into it. And so if you want to say that variable A in cell 1 is variable B in cell 2 subject to transformation, you can define a relationship just like that one that we have in antimony. And it'll handle it automatically. And that's definitely a feature that is very attractive. And they had the benefit of our experience. It's the second mover advantage. A lot of the language features they have are similar to what we have. But since their code was developed after ours, they were able to see what was missing. And I've been tempted to try to actually adopt their model specification language. It's very beautiful, but it's a big job. A lot of their code actually can be translated into Python pretty easily. They have a few concepts that don't map easily. And that connector one is specifically one that's tricky. And it means that the way their language is processed is rather complicated. They have to do lots of parsings. They have to parse it and then look for unresolved symbols and then parse it again and parse it again. Their parsing algorithms are pretty complicated. Beautiful, really, really good software engineers. Okay, so to specify models, typically we're going to use antimony, intuit it, and then run them inside of CompuCell. In the old days, before antimony, when you used Spml, the disadvantage of Spml was you didn't want to write it by hand. And so you had to use an editor like Copazzi. There are others that are graphical or text editors. Tellurium will output SBML, so you can convert. One of the things in your cheat sheet is to convert antimony to SBML for interchange. In either case, you can load it into CompuCell, but this is historically why you'll see SBML instead of antimony in a lot of our function names. Okay, so our steps. First thing, define your antimony model as a string. We know how to do that. We've done that last time. Again, we can have multiple different antimony models inside a single cell or in the model background is free floating. Different cells could have different models in them. So we have complete flexibility that way. It's generally a good idea to give a different string name to each model. Don't use the same name twice. One thing that we will have to do is that antimony has a concept of time, and CompuCell time steps in a very naive way. It just does time slicing. And we saw this when we were looking at the diffusion solvers. Secretion, we had 3 ways of doing secretion, and they were done sequentially. In the same way, there's a pot step which moves the cells around. Then there'll be a secretion step, then there'll be a diffusion step, and the antimony steps will be interleaved with that. And so what we have to do is we have to say how much antimony time do we want to run per Monte Carlo step. And that's a parameter that you have to decide. It'll depend on what units you use to define time inside your antimony model. You can have different time scales for different antimony models. But you do have to keep track of how much antimony time in each model is in one Monte Carlo step. And so you should keep track of CC3D units and conversion factors. So typically here you'll have something, ideally you put it at the top of your steppable so that it's available as a global. SBML step size equals some conversion factor, days to Monte Carlo steps. If the units of time in the antimony model were days, minutes to Monte Carlo steps if they were minutes, seconds to Monte Carlo steps if they were seconds. But it's a good idea to have that definition somewhere so you could refer to it. Okay. Then you want to load your antimony model somewhere. Here, I typically, again, put that model string in that top level of my simulation after I've done all my imports and everything else. ODE model string equals, and then my antimony. That way it's available when you need it. Okay. Once you've got the model string, you typically will load the model in your start function. And as I mentioned, there's a variety of scope that's possible for loading models. Remember, with secretion and uptake, there were lots of options because you could secrete everywhere inside of the cell. You could secrete at the surface of the cell. You could secrete inside the surface of the cell, so on. There are a number of options that we have here. Ultimately, they all do the same thing. Self.add antimony model to cell. Model equals model string. Model name. You have to give it a name, a handle. Which cell you're loading it into, and then that step size conversion. We're going to do 1 Monte Carlo steps worth of time stepping. How far in units of antimony do I run? We can load into cells by cell ID rather than by cell handle. Sometimes that's convenient. We can have a list of cell IDs, load into cell number 1, 17, 37, 98. We can load it into all cells of a given type. Or we can load it as a background model that runs free floating in the simulation. That model name, just the way we need a handle when we do plots, that model name is important. We'll use it a lot. Step size specifies the conversion from antimony time steps to MCS. We can also read the model if it's source saved in a file rather than in text in line. We, instead of saying model string equals model string name, we could say model file and then its path name, and it'll read it in. We can also define initial conditions. We can overwrite the initial conditions in our antimony string if we want to. As an example here, and it can be more complicated than this, initial conditions is a dictionary. Not surprising given that we're doing everything with dictionaries. Initial underscore conditions, variable S1 equals whatever, variable S2 equals whatever. And we add to antimony model load, initial conditions equals, and then that. That will overwrite whichever variables or parameters we specify. The ones that we don't specify will use the defaults that were given in the model specification. And again, this is a little different if you're, Python allows this kind of overloading. So you do it in Python. I'm sure C++ allows, well, I don't know how much C++ allows it. Probably some. In these kinds of declarative languages, this kind of overloading is very usual. But if you haven't done it, it may take a little bit of getting used to. As usual, Twit provides code snippets if you're using Twit. I know TJ doesn't like to use Twit because he likes to use things that are more GitHub friendly. I like Twit because I like having the code snippets. TJ has been trying to work to get Visual Studios to have code snippets. It's no fun. Really no fun. Here, there are these SPML solver routines. Again, SPML rather than antimony as a name. And there are quite a few options here. Specifying initial conditions, adding antimony models, cell ML models, SPML models. This is a bit old. There are now MabBoss models also you can load. You can add them to individual cells, add free-floating ones, time step them, copy individual ones, delete them. And you have options for what the integrators look like and a variety of other possibilities. I've used a lot of these, not all of them. There are a lot of options. For our purposes, we won't need all of them. So we can add a free-floating model. We've seen the text, self-add free-floating model, and the options for that. Again, that typically will go in the start function. It might wind up somewhere else. It might wind up in a step function. If I create a new cell in a step function, I might do the same thing. Okay. Again, what's important is model string, which is where I specified my model, my subcellular model. Model name, which is going to be how I'm going to reference it. And I'm going to use that a lot. And then the step size, the integration step. Okay. Once I've loaded the models, I time step them. The reason that step size is important when I have multiple models is that CompuCell does not give you the option of time stepping parts of some of the SPML models and not others. There's a single time stepper that time steps everything together. That's simple, but it means that if there are different time scales, you have to keep track of them by hand. So self.timestep_SPML will time step everything one Monte Carlo step per time forward. There are some options for the integrators. If you use the SPML or antimony, occasionally you'll get things like CVODE errors. CVODE is the backend solver that's used. And so you can get convergence errors, and you can change the accuracy thresholds, for example, for the ODE solvers, if you want to. And so there is something called self.set SPML global options that allows you to control the specific details of the integration. I hope you don't have to deal with that. In practice, if you do have to deal with it, it means you're doing something pretty hard. And we can come back to it, go over that in more detail. So again, time stepping, Twit has the time step command built in. That usually goes in your step function, self.timestep SPML. It's usually at the head of one of the step functions. The next thing that we have to be able to do is read and write values. If we have no access, we don't get anything useful out of it. Again, references for a model loaded in a cell, cell.spml, and that model name, which we specified when we created the model, loaded the model, instantiated it, and then a square bracket, the name of the species or parameter that we're going to read. We don't have to do a get and a set. In the old days, we did. These days, they're dictionary entries like anything else. They can be read and written too. If the model belongs to the simulation as a whole, not to the cell, it's self dot, but the syntax is otherwise identical. I can say variable equals, if I'm reading it out, cell.spml model name, species name equals value to set the value. Nothing complicated going on there. If we want to read out the full state of the model, there is model name.values that will return the whole dictionary. And I actually don't remember the exact format of that. I'd have to print it and look at the exact details of how it works. I don't use that one very much, but it's potentially useful. The one thing that you may run into is something that we do a lot, and you probably want to do when you're working with subcellular models, which is that to see what the state of the subcellular model is, it's very useful to use a tracking field. As I mentioned, my favorite thing about CompuCell is the tracking fields. We say create a tracking field, we give the key for the variable name, and then it automatically displays things. However, that won't work with a SPML model, because instead of cell.dict and the name of the species, we have cell.spml.model name of the species. It's a different dictionary. And so if we want to do a tracking field, we will have to write cell.dict parenthesis name equals the thing on the right. So we have to do that. That's why I was saying there's a little bit of glue code we have to write. We have to do those things by hand. Okay. So setting and getting values are there. They're simple, but they're there in the Twitter if you need them. And here's what they look like. It's possible to copy models. We can copy them from a cell to another cell. Why would we want to do that? Well, when we copy the model structure is easy. We could reload that. But the values of all the variables and parameters might have been overwritten. And we wouldn't know that except if we pull it out. And so it's helpful. If we really want to clone simulate the state of a model, of a subcellular model, we need to be able to do that. And so that's actually quite a powerful function. And there are a variety of options that we have for doing that. We can copy all of the simulators, or only if we had multiple submodels written in, we can copy just the ones we want. And then, as I mentioned, we can delete models as well. That's not something we run into very often, but for example, if a cell differentiates and it stops doing some complicated thing that we had loaded before, we might want to stop doing that and do something else. Okay, so let's actually do a little bit of an exercise. I think the way I'm going to do this is I'll give you the exercise. I want you to think about it, try it out. And then I've got a set of slides that'll walk you through my solution to it. And then I want you to go back and finish it up if you hadn't done it. So what we'll do is I'll give you the exercise. I'll give you 5 minutes to try it. I'll walk you through my solution slowly. You can try doing it sort of on the fly. And then I'll give you another few minutes to make sure that it works. How's that? I'm always a little bit torn because if I walk through just straight through, I don't know how much. I think it's worth trying it for a few minutes first to see where you get stuck, and then you'll maybe appreciate it more. So the idea here is, let's just create, this is just going to be a free-floating model to begin with. Create a basic simulation template, 2 types of cells, proliferate quiescent. Give them contact and volume energies, target volume of 125, just use the XML for that. You don't have to specify it in the Python. And now in the Python, create an antimony model just with A goes to B at a rate K1 times A. B goes back to A at a rate K2. That really looks to me like it should be K2 times B. So I may have a typo there, but we'll see when we go further for it. Load the antimony model as a free-floating model and see that it time steps. So put in the step function the time step. Retrieve the data from the free-floating model and plot as a plot, scientific plot, the values of A and B. And then at time 1,000, multiply the value of A by 10 and keep plotting. Is that clear? In fact, the code we ran last week did all of this. It's basically this, but I'm asking you to try to invent that on your own. The code last week was a little fancier because it had some extra dictionaries and things for doing plots. But is that a clear exercise? So why not people take a few minutes, 5 minutes, and give it a try, then we'll walk through it together and I'll give you time to finish it up. And I'm going to get some more water because I'm getting hoarse.
Should we have initial conditions for A at least?
Yeah, they're definitely pick a value for A, yes. If you start out with both A and B 0, it's going to be pretty boring.
The target volume, I assume, is for the proliferating cell, right? Or both of them should have a target volume of 125.
Yeah, at the moment, we're not going to have any proliferation. It's just at the moment they're uncoupled to each other. The cells of the antibody aren't doing anything.
They're not. Yep.
So it was just if you're going to create the cells, you got to give them a volume or they'll disappear. So eventually, we'll gradually start with this and then make it more interesting. But this is just to get the basics working. So maybe let me just show you the couple of slides I have, and then you can come back to it. So the first thing I did was just to try to create a XML for target volume of 125. I call them proliferating quiescent, but they're just sitting there doing nothing, but they're two colors. So. Then I had a basic antibody model. And sure enough, I left the B out in my rate. I knew it had to be wrong. And so if people want to copy that, that's okay. You don't, as I say, I prefer to always put the comments in, but you don't have to put the comments in if you want to save some time.
Yeah, I'm ready to move on because I'm
Okay.
stuck in another place here.
Okay, so then in the start function, I would say I want to instantiate my model. So I do self add free floating model antimony. And then my model string is by the name of my model string. Give it the name my model, step size of 1. And then a step function step dot time step Spml. And again, you don't have to type all that because it's in Twit if you're using Twit. So you can. And also the SPML model definition you can also do in Twit. So the boilerplate for all these is available. The key thing is you have to remember what you called the model string. And if you give it a model name, you have to remember what the name is. And then, oops, there's that didn't display right. You have to add some plots. And then what's more interesting, and I apologize for the format issue here, I don't know why the box isn't displayed properly. Yeah, after you've stepped your model, you can say A is self.spml.myModel of A, B is self.spml.myModel of B, and then add A and B to the plots. So now you're reading out the values from the SPML model. Again, I recommend using the Twitter to boilerplate those in. And you put it together, you should get that. And you can tell that I didn't write this particular one or run it because it's on a Mac. So I'd have different windows. Well, I did write it and run it, but I didn't cut and paste new versions of it into the slide. Okay, if people want to go back and look at the problem specification, that's fine. Or if you want to see any of the particular slides, we could go back and look at those together. Or if you need help and you want to go over something you're having problems with, that's fine too.
Yeah, can we go back to that where you show the SPL we are addressing? Yes, that one.
This
second,
one?
No, the first, the penultimate that you were showing.
Sorry, not this one?
Not this one, the one front. Yeah, that one. Okay. Thank you. Oh.
If you've got this working already, go ahead and do the last part of the exercise, which is at time 1,000, make A 10 times as big as it was. That takes a grand total of 2 lines of code. In the old days, when we first did this, the integration still was more like what we have to do with the some of those XML parameters and variables, where you have to do sets and gets. So you had to define functions that did set and get for things. And that really is not convenient. And so the fact that the antimony variables and parameters are available just as dictionary entries really makes things a lot easier. Because you don't have to, if you want to increment value of A, you could say self.spml.mymodel times equal of A times equals 10, and that'll work. You don't have to do anything elaborate.
Go back one slide, please.
Sure. If you really got ahead of us, you could try changing it to load the SPML model in not, or the antimony model, not into the free floating, but in each cell individually. If you're waiting for people and you're ahead, you could try that. But it's always going to be basically the same logic, which is you define the model, you load the model free floating or into particular cells, you time step it, and then you have to have some way of reading and writing values from it. Is anybody else having issues or need help with something?
I definitely have an error, but I'll try something else here.
So here was what happened when to make that change. Here I set it equal to 10 instead of times equals. I said multiply it by 10. Instead, I set it to 10 here. Same idea. And if anybody has a problem, wants to show their code and look at it together, that's fine too. Because I do want to get do one or two more things before we run out of time. On the other hand, I don't want to leave anybody behind, because if we can't do this basic thing, then the other things will be frustrating. So
I'm in
Joel,
this. Oh, okay.
Connor, if you want to show what you've got now.
Well, I was going to say I'm in the same boat as Joel, where I'm hunting down a bug that I haven't found yet.
Well, we can look at it together. That's fine.
Joel, do you want to go first for the debugging?
Yeah, maybe it's the same one. Let's see. I'm getting this a file or so I didn't give the path. I just give the name of the model here.
Yeah, yeah.
So it should be okay. But then I'm getting this Roadrunner error.
Okay, let's look
Saying
at the code together.
okay, let me share the correct screen. Should probably share the whole screen.
Okay. Ah,
So
that's easy. Where's your model definition?
it's outside the class.
Okay, let's see. Well, maybe it's not easy. Let's see. Equations. Equations, fine. Model. Add
Mhm.
free floating SPML. Oh, because you loaded as SPML. It's antimony.
Okay. Thank you.
So this is a confusion. I should have had that as a red warning in my slides. So most of the time we use SPML for everything, but when you're doing this is a parse, and so you
Okay.
have to tell it which language you're parsing from.
Gotcha.
So
Okay.
try free floating antimony and see if that fixes it. Connor, what about you? Is that you want to show your?
Yeah, that unfortunately was not my error, so I don't get to freeload off of that debugging. Okay, so I declared the model up here.
Yeah.
And then here I have free floating antimony with the string
Right.
being model and the
That
model
looks
name being
fine.
AB reaction.
Okay.
Initialize my plot here.
Right.
And then I have self.spml AB reaction is A. And then I have that. Oh, I just debugged myself. I know exactly what's wrong. Give me 1 second.
I think there's some square brackets that don't need to be there.
Yes, that is exactly what's wrong.
Well, that's why an extra pair of eyes is good.
Yeah, I'm all good now. It was square brackets.
Okay. Joel, what about you?
I got it. Yep.
Anybody else need help? Everybody okay? Okay. So now your next assignment is to load the antibody models into the individual cells instead of free floating model. And I would say, since we don't have that much time, I wouldn't try all of the different options. I would just load the model into all of the cells. But I do want you to add 2 tracking fields. And remember that to do that, we'll have to create a dictionary entry in which you're going to move the value from the field, from the subcellular model into the dictionary entry. Okay. And so if you wanted to do something more fun, you could have the proliferating cells grow and have the rate of growth be A or B. And now you're beginning to build something that's a little more useful. Or you could have the proliferating cells grow at rate B and the quiescent cells grow at rate A. So then you'd see something where they're not the same. Okay, is that working for people? So here, I just want to remind you, there are a lot of options for loading into cells. I would just do the load all cells one. It's the easiest. For cell and self.cell list, self add antimony model to cell. Notice the only thing that you need to do here, there's actually a typo here in my slide. I apologize. It's a cut and paste error. This should just be cell equals cell here. I cut and pasted the line above it. And again, that reference is available in the Twitter. And then I added the track attributes, field name A and A. And then you have to do in the code, you'll have to create a dictionary entry for A and B. And then you have to copy from the Spml into the cell-based dictionary. And this is something that we didn't talk about much in class. It's definitely Pythonic rather than compucellic, which is that if you're referencing the SPML model, it's possible that some cells might not have the model loaded or might have a different model loaded. And so it's not unreasonable to think that this assignment could fail because this reference to SPML model could be not present. And so try and accept key error will trap that so that the program doesn't break. Suppose you loaded only the SPML model only into cells of type proliferating. And then you tried to read the value from a cell that was of type quiescent. That would crash CompuCell without a try except. In our case, if you're loading it into all cells, you shouldn't have that problem. But in principle, I'm not recommending writing code where you don't know exactly what's happening in each cell. But when these models become complicated, occasionally using these error traps are not a bad idea. And then you get something like this. Here, I did it just in a single cell. And you'll notice here that trap is needed because most of those cells don't have that attribute. Here, I loaded it only into one cell type, into the proliferating cells. Here I loaded into a cell rather than a cell by index, and here I loaded into all cells. Again, as these models become more complicated, especially when you're going to do potentially a lot of different submodels, keeping track of everything isn't always so easy. Again, it's better to keep track, but having that trap is useful. Were people able to get either into all cells or into all cells of a given type to work?
I had a question.
Sure.
So I'm just trying to put it into one cell right now. It says when I run it that my initial conditions is not defined.
Okay, let's take a look.
Oh, I don't want. So, yeah.
Okay. Ah. Okay, so you've used the initial conditions option when you loaded the model.
Okay.
But you don't need that. That's optional. But if you ask for it, you have to specify it. So I would just eliminate that initial conditions equals initial conditions, because you're not overwriting. That's to overwrite the parameter values in the original in the model specification string. So try that now. Okay, so now cell number 20 is not defined. That's a different question.
I don't.
So that is.
Oh, I didn't change this to 1 also because I don't know if I have 20 cells.
Okay. There you go.
I haven't made my field yet. The initial conditions was throwing me off.
Okay, that's fine. Great. Anybody else have a comment or suggestion on that? It definitely takes some getting used to, and that's why I like to do these very simple exercises first, because if you can practice a few times with the very simple ones, then going to the more elaborate things becomes easier. And as I say, if you've done that, if you've got the base model working, you can try something where you, for example, have cell growth or cell target volume depend on A and B, ideally differently in different cell types. Or you could go the other way. You could have A and B values depend on an attribute of the cell. You could have the A changed by the current volume of the cell, as an example. If you're really ambitious, you could try having the cell divide and then copy the model from the parent to the daughter cell. I wasn't planning on doing that one today, at least not in these exercises. When you do the cell division example, you need to do that, but I wasn't going to do that till a little later. And again, if anybody has a question or needs to see a different slide, just speak up and I'll do my best to help out. For reference, if you do it, if you're going to do it where you load only one cell or only one cell type, then you will need to use the try and except when you try to copy the cell dictionary attributes, because they will only exist for some cells, not for all of them. So that's not syntax we've gone over before, so I'll leave that up. Paxton, is that working now for you?
So now I'm getting error as a file or URI.
Okay, let's take a look.
Okay.
All right. So there are two things. First, you're loading. Let's see, where's your load call?
Like in here.
All right. That looks reasonable. Free floating. Oh. Okay, you're adding free floating antimony model. Where are you adding the model to the cell?
I did this one down here. Do I need to get rid of this?
Yes, you can't, well, it should be all right, but let's look at the other one. Modeling, model.
Well, you're adding the model in the step functions. It's gonna not like that.
Oh,
Oh, you're over, yeah, you can't load the same model twice at the same cell.
so I need to
Thank
take
you,
this
Alex.
out and put it up in the start function.
Yeah.
And then comment this one out.
It won't do any harm, but you don't need it. Yeah, you comment there.
Okay.
Also, you're adding an SPML instead of antimony. I don't know if it'll work.
Do I need to make this be add antimony?
Yes.
Okay.
Let's see. Are we using that free floating model somewhere else? Hot window, that looks okay. That looks okay. Oh, there's no self.spml model anymore in line 77, but that's not where it's crashing. Okay, so 59 and 60 won't work because there is no free floating model.
Okay.
Line 77 won't work either because they're all inside of the cells now. And now you don't have
The plot. Yeah.
Okay. So then I just need it.
I don't think you want to be plotting the time series anymore. I mean, it's okay to do that, but
Oh, all right.
you created the tracking field.
Yeah, I got it.
So let's think about this a little bit. Let's come back to the code that we wrote. So we have to do is the first thing we have to do is let's just start from the top of your code. You create your you create your model. That's fine.
Mhm.
You have the tracking fields implemented or not?
They're right here.
Okay, so they're in the init. They're fine. So you create the tracking fields. That's fine. You create the dictionary entries for them, that's fine. You add antimony to all the cell type proliferating, that's fine. You create the plot window, which we're not going to use probably. That's okay. Okay, now in the step function, we time step our SPML, that's fine. And now what we have to do is we have to copy the value of A and B from the model into the dictionary entry. So we'll have cell.dict of A equals cell.SPML dot, and so on.
Wait, cell dot, not self dot?
Because now it belongs to a cell. So now we're going to have a loop over the cells. We have to create a loop over the cells.
So would I say for cell?
Cell and cell, right? And self.cell is. And you probably want it to be list by type because you only have the model loaded. If you don't want to have to use your try, you'll have to do it only for the cell. Okay, so remember in your CC3D Python code snippets, if you don't remember, go up to CC3D Python at the top. Yeah, there you go. All the way at the bottom, visit all cells of a given type. There you go.
Okay.
So now you'd say self dot proliferating. Okay. And now you can get rid of 63, 64, 65, 66. Yeah, there you go. Let's see if that works. Missing.
I don't need this anymore.
No.
I don't need that at all. So
There you go. Now see if the tracking field works. Okay, not so exciting, but it's there.
okay. Then I can just mess with it.
Great.
You-
So again, I mean, it's one of these things you have to, it takes some practice, but how about other people? Were you able to get that to work? Everybody? Great. All right. Okay, so I don't know if we'll have time to do this whole exercise, but it's a homework problem. So one of the things that we've talked about signaling by diffusion. Cells signal to each other a lot by contact. And there are many different kinds of contact signals. Cells can have what are called gap junctions, which actually pour chemical from one cell to another directly. They can signal through secretion and absorption the way neurons do. Locally. They can signal by contact. They can actually assemble fibers between cells, for example. But one of the key ways that cells signal is through a mechanism called delta and notch. And delta and notch are a pair of transmembrane proteins that have a rather specific pattern of interactions. In particular, delta likes to be next to notch, and notch likes to be next to delta. But delta doesn't like being next to delta, and notch doesn't like being next to notch. So if we were on a nice square checkerboard, you'd get a checkerboard of high delta and high notch cells. On a hexagon, the thing is frustrated. You can't get all of those satisfied at once. And this kind of delta notch signaling is important. It shows up in stem cells regulation and colonic crypt. At the very beginning of this course, we ran that colonic crypt simulation without looking at what it did. And delta notch typically gives rise to this kind of salt and pepper patterning. In this case, they're hair cells of Drosophila ear. In this case, it's the eyes and the cells in the eye of a zebrafish. In this case, it's human intestinal crypt. Many mechanisms differ between insects and fish and humans. In this case, delta notch operates in developmental patterning and in maintenance of adult tissues in all of these different species. And so these are transmembrane proteins, and they're what are called a receptor ligand pair. That is, delta binds to notch across in trans, that is across pairs of cells, and notch binds to delta. And when notch binds to, when delta binds to notch, it activates notch and sends a signal. And there's some intracellular signaling going on. Activated notch inhibits cell specialization. It keeps cells in stem-like state. Activated notch inhibits the production of delta. And in general, what happens is if you have two cells that are initially symmetric, one will go high notch and one will go high delta, and you'll get a checkerboard pattern like that. In fact, as our friend Lorenzo Veschini at King's College London has shown in his experiments, you don't necessarily get a static pattern. You can get flickering where cells go from high notch to high delta. You can get waves of high notch and high delta, depending on the details. There also are some additional complexity that delta and notch on the same cell bind to each other and inhibit each other. So basically, if you have a lot of delta and notch, if you have a certain amount of delta and notch, they annihilate each other and leave whichever one they had more of. So there's also a cis interaction, which we're not going to model. Now, the actual pathway is a little bit complicated, but there's a simple model by Collier, which just has two components. Every cell has delta and every cell has notch. Delta is produced at a rate that decreases as the amount of notch goes up. That is, notch inhibits delta. And if I were being consistent, my arrow would be a T arrow here rather than a pointy arrow, but I'm copying from the published paper. It doesn't use the right notation. Notch is activated by delta. So the more delta I have, the more notch I get. And in both cases, I have first order decay, delta decays, notch decays, and I've set the time constant to 1 for that. And there's some additional parameters. I need to know the scale of the inhibition of the activation for delta, for notch by delta here. It's set to be 0.001. I've got the scale of the inhibition of delta by notch is 100. I've got these Hill coefficients 2, which means it's fairly smooth. And I've got this rate constant, which is set to 1. And if I run this, I get this nice checkerboard like that. Well, hexagonal checker. Okay. So, why don't we try this? I think we're going to run out of time, but we can get started. But why don't I walk you through? Why don't I walk you through it? And then it'll be a homework problem. The homework has been assigned. So I want you to create a small simulation with a single kind of cell. And we're going to fill the cell with initially square cells. It's actually less interesting when they're square, but we'll start with square cells. With 4, so there's with 7, so 7 by 7 cells. And it's 42 by 42, so there's 6 by 6 of these. And now we're going to write an antimony string that's going to correspond to these two equations. And you can write them as explicit ODEs if you like, or rates, either one. And then we're going to load the antimony model into all cells. And we're going to give the initial concentration in each cell of delta and notch to be a random number between 0.9 and 1. And then we have to ask the question, how much delta signal do we get? Because you'll notice that this delta here is not the amount of delta inside my cell. It's the amount of delta coming from my neighbor. And so what I'm going to have to do, this got a little bit messed up, this format, this line should be over the D, not over there. What I'm going to have to do is I'm going to have to do my usual iteration over cell neighbors. And then I'm going to have to read the amount of delta on each neighbor. I'm going to have to add it up and average it. And so that's going to be the trick in this simulation. For each cell, I iterate over my neighbors. I read the amount of delta in my neighbor, and I pass that into my internal signal. So this is answering Connor's question from earlier, which is how do I connect adjacent cells to my cell? So it makes you think about that a little bit. Okay. And then we're going to create auxiliary fields to display delta and notch in each cell. And so here I've created a 42 by 42 domain with a single type of cell. I filled it with cells that are 7 by 7. They're going to gradually change their shape as time goes on. I'm now going to write the antimony model corresponding to my two equations. Here's what it's going to look like. J1, nothing goes to N at a rate D average, because that's the external D, to the K over A plus D average to the K. Nothing goes to D at a rate V, 1 over 1 plus beta times N to the H minus T. The average, that's going to be substituted from my measurements in the simulation, but I have to give it some initial value. Initial values of D and N, I mentioned I'm going to overwrite those. And I have to give the parameter values. Okay. Then I have to load the antimony model into each cell. I don't really need to do it by type here because I'm doing it into all cells, but I might want to do it by type. And then I give initial values for D and N picked from a random distribution between 0.9 and 1. That means that I have to have loaded NumPy, so I have to remember to load NumPy. And I time step it. And this is going to not do anything because that external value of D average isn't presented yet. And so now I have to calculate that. I go through each cell in my list. I set D average to 0. I set my number of neighbors to 0. I iterate over my neighbors. I read the value of D from my neighbor, add it, and then I divide and accumulated. I could probably do this in a more Pythonic way, but I need to get something that's an iter. I could pull this in as a list and then do mean and standard deviation instead of doing the average by hand. Okay. I create a tracking field for D, a tracking field for N. As usual, I have to copy the values from the dictionary entries for the submodel into those for the cell to get the tracking field to work. And I'll get something that looks like this. Initially, I'm going to get D and N both being large, between 0.9 and 1, because that's where I set it. As things run, I will get the salt and pepper array where the high deltas are isolated, surrounded by high notch. And because this pattern moves in time a little bit, you'll see that the pattern will fluctuate. And so occasionally one of these high delta cells will flip, become high notch, and vice versa. And depending on how big the system is and the exact parameter values, you can also get situations where the cells get stuck in intermediate values or where they oscillate continually. So that was really the exercise. The last thing I wanted to talk about is we're going to be running out of time. So we're not going to, this exercise will be a homework problem. We'll have the slides. Is something that I wanted that you people will need for the applications, for the NanoHub applications, which is steering panels. So we've done changes of values, of parameter values, while the simulation ran using that model editor window in Player. And in principle, we can make some of those model editor functions available using the XML, connecting it to Python. In practice, that's not so convenient. And so if we want to change Python variables and parameters with a decent user interface, CompuCell gives you a limited number of controls through what it calls the steering panel. And this is something where if the user is not going to edit your code, they have to have some way of being able to change things while the simulation is running. And so the steering panel is not the most flexible, it's not the prettiest in terms of its layout, but it works. One thing, again, just the way we had to think about declarative programming is something that's a little different in terms of the way it works from procedural programming. Steering is event-driven, and so you have to think about that. If you're not used to it, it may be a little bit unexpected how it works. To use the steering panel, the first thing we have to do is create a steering panel window and define the parameters that are going to be modified. We have to define a function that watches for panel updates and reports them. And then after they're reported, we have to change the value of the updated parameters. Because the steering panel may never be touched, in which case it never comes into action. It only is touched when somebody actually goes in and manipulates it while Player is executed. In principle, there are a lot of different steering panel options. And if people have used NanoHub, Tellurium, or Jupyter Notebooks, you'll know in IPy widgets gives you all sorts of steering options. CompuCell only implements a couple of them. In particular, it gives you a combo box, which gives you lists, pull down lists, and sliders. And to add a steering panel, I don't know what happens if you try. I don't think you can add more than one because it doesn't have a name. So I think you can only add one. It's not like a plot window where you can add multiple ones. Between the init and the start function, so after the init, we'll do a def. So it's a function. And the def is add steering panel, and it's as argument self. And within that, and this is code that I took from a simulation I wrote that's up on NanoHub. But it has examples of the kinds of things that we'll do. We're going to add, each time we add a steering parameter, it adds a line to the steering panel. And again, there's Twidit has all the boilerplate for this. In this case, we'll create a steering parameter. In this case, I called it simulation type. The value will be displayed. And then, because this is a list, a pull-down list, we have to list all the options. And here I've given it 2, neutral variation and simple somatic simulation. And the widget is of type combo box. So I could have 10 options, 20 options, as many as I want in a pull-down menu. The other thing I could do is to change a numerical value. Here I've got a variable named killing efficacy. Its default value is 0.5. I can set a range, minimum value and maximum value. I can set the decimal precision with which I display it, and this is a slider. That will pop up a window. It'll have 2 lines in it, the first one of which will be labeled simulation type, the second one which will be labeled killing efficacy. And the first one will allow me to pull down and select between neutral variation and simple somatic simulation. The second one will allow me to pull a value, initially 0.5, and I can make it minimum of 0 and maximum of 1. And it'll show the result at 2 decimal digits. If you don't limit the decimal precision, it'll make a mess because it'll display a lot of digits. Then I need to create a function that actually processes this. And the process steering panel makes me, I have to do something. In this case, I'm not referencing the ones I just did. I picked a different set of examples. But here I have something like a variable named target volume, and I have a function which is self.get steering parameter target volume. So what this will do is the function process steering panel data will be called anytime somebody manipulates the steering panel. You don't know when that will be because it's an event-driven, user-driven input. When it does, you go in and you read the value here of target volume. I would have had to say something here. Name equals target volume, range of values. And then I can transfer that value from what I've read into my parameter. Notice that because this is inside a function definition, I need to do something with target volume because target volume is local to that function. And so I could either write target volume into a dictionary entry for self.dict, which would get it out of the function. I could write it into cell.dict if I wanted. If I want to make this available otherwise, I have to do some global that allows me to transfer that information in and out, which I don't recommend. And so that there's a little bit of a trick to being able to use these steering panels. So here's an example of something else that one can do. It's often nice if you're doing complex simulations, especially for something like NanoHub. Instead of having 5 versions of your program, the person has to load and run them separately. You give them an option to select which kind of program they're going to run. Am I going to run the one where I load my SPML or antimony model into a single cell, into all cells of a given type, or into all cells. So I could create a pull-down window, a pull-down menu that allows me to select which of those I want. But that's typically something I do at the beginning of the simulation. I want to do it once. And so one way to deal with that is to create a feudal loop where I say in my step function, I read my steering parameter value. And if the steering parameter value is some default, select simulation to run, I just keep pass. I keep coming back. If the user has pulled it down and selected a different one, then I assign the value and I start my simulation. Does that make sense to people? Another thing I might want to do is I might want to have the user first set a bunch of parameters, initialization parameters, before they set which simulation to do. So I could say, here, I read the value of probability p mutation. The user does that once at the beginning, and they shouldn't change the value of simulation type until they've got all the other ones set. So you have to tell them to do that. But this way they can select all the initialization values, then say start simulation. You could have a button that says start simulation, pull it down, start simulation, then simulation starts to run. It's not very elegant, but Player was never really designed to be used in a lockdown mode like Nano. So does that help people a bit if you're thinking about how to present a simulation to the world?
Yeah, I have a question. Do you have to, there is a way to reinitiate the Monte Carlo step to 0 if someone changed the simulation in the middle of it? Or they have to press stop and.
So tell me what you mean. I'm not
Like
sure.
if someone in the middle of the simulation is running, select a different module, will it reset the whole thing, or do we have to do that also manually? I'm assuming manually, right?
Here in the way this is written, if somebody changes the type of the simulation after it started, it won't do anything.
Oh, okay. Yep.
But there's no reason that you can't have your pull down menu update something that's meaningful to change in the middle. But that's a question of how you design the code that you're going to run. This was specifically for the idea of, I want the user to have to pick a bunch of parameter values and then tell me to start the simulation. There's no reason that you can't, during the simulation, change the value of parameter such and such from 22 to 24, if that's meaningful. Just the way when we're running the simulation, we could go and edit the value of lambda chemo in the model editor. But the point of the steering panel was really that the model editor only exposes the XML specified parameters. And so we wanted to be able to have the user edit during the run any parameter. It's more work because they're not automatically exposed. You have to do it by hand. But if you know that the user should be able to edit lambda chemo, V target growth rate, lambda chemo, and saturation value, then you put those in the steering panel and have those available. Any other questions? We're over time and people are getting tired, so I don't want to keep people. But I thought I did want to show these basic methodologies because when you're designing a NanoHub app in particular, they're useful to have.
I do have oh, sorry.
Please go ahead.
So something that granted you know what the current state of the simulation is, so I don't know for sure yet. But one thing that we're coming across is that between the season lengths that they implement in the paper and how it runs, it's incredibly slow. Will that be okay for NanoHub? I think it's going to be the type of thing that might run for a pretty long time.
Well, so it won't be ideal. And it means that maybe the people who maybe you won't get a lot of users. One thing you can do in NanoHub is you can request 4 cores. So you can multi-thread it to at least 4, and that should give you a little bit of a speed up. You can make the simulation smaller, so they run faster. But this is always a bit of a problem because, especially for evolutionary simulations, you tend to have to run a lot of generations. And if you crank up the mutation rates too much, then funny things happen. They don't behave the way you want. And so it may be that this isn't the ideal thing to demonstrate in a live simulation. It may be something that's better to run batch. But that's okay. I mean, for the purpose of the class, as long as it works and that it demonstrates the idea, that's okay. But it is a limitation. So most of our NanoHub simulations that we write, we do in 2D, even though they might be more informative in 3D because they run faster. Or we run them on a small box. One thing that's a problem, a little bit of a problem, you can do it in CompuCell, but it's a pain, is that you don't really have a way of having the user select the size of the simulation. Because once you get to the point where the user has an interface, it's already set the X dimension and the Y dimension. Now there is some code in CompuCell which isn't used that much, which allows you to redimension the cell lattice. And if somebody really wanted to be adventurous and say to the user, you tell me how big you want the lattice to be, type in the value, and then I'll reset the lattice, you can do that. That's a little more, that's a little bit more on the user interface than I would ask people to do. But I agree, the problem for you is going to be that particular adhesion rule that you've got is going to be slow. And I don't know if you went down to 6 species or 10 or 5 species instead of 12 and 12, it might be faster. But I think that I would do what you're doing, which is replicate the model as written as closely as possible. And if it's too slow, then ask yourself the question, no, as a exercise, generic exercise, that's fine. If people run it and they let it run overnight. As a NanoHub demo, could I write a simpler version of this that ran a lot faster that would still get the core idea across? But the first thing to do is to do the replication. I wouldn't worry about the simulation time. Okay, great. Anything else we want to go over tonight? I hope that was helpful to some extent. I see there a number of typos in the slides. I'll try to get those fixed. And I appreciate your patience. I look forward to seeing what you guys have next week. And I hope people, I know people are going to be working 90% on their projects, but I did do this one assignment on delta notch because it's such an important simulation. And I'd like people to spend an hour trying to get that to work. It's really pretty. Okay. Good night, everybody. Thanks for coming. Okay.
Right.
Bye.